this morning is Peter Lodahl. He's a professor in Copenhagen, and as well as the director of the Center for Hybrid Quantum Networks. He received his PhD in Copenhagen in 2000, and then went off for a postdoc position in Caltech, if I remember correctly, as well as Twente. And then he returned back to Copenhagen to become a full professor. And he will talk about photonic quantum technology, how to deterministically deal with photon generation, for example, as well as deterministic entanglement of photons. I'm really much looking forward to the talk. Thank you very much.
Thank you very much. Can you hear me? Yes, perfect. So thanks a lot for this kind introduction, and it's a real pleasure to be here. It's a pleasure to be out in the real world again and travel and see real people. So we generally enjoy that. I'm coming to you indeed from Copenhagen, from the Niels Bohr Institute, University of Copenhagen. So we used to brag about that this is where quantum technology, no, maybe not quantum technology, maybe quantum science was born in Copenhagen at the Niels Bohr Institute. But this is 100 years ago, so you may ask, so what has, maybe there's some truth to that Copenhagen back then was the center of quantum, but you may be interested in what has been going on in Copenhagen for the past 100 years. I won't cover that, but I'm going to say a little bit about what is going on, in particular my part of the group or the Niels Bohr Institute that is working with photonics and photonic quantum technology. And our speciality is to produce, indeed, deterministic single photons and entangled photons on demand, and also think about what kind of quantum computing architectures, quantum communication opportunities that hardware that we are developing, what that enables. So we'll take it slowly, and the more feedback I can get from you, the better in terms of am I hitting the right tune, or is it too boring, or is it too advanced? It's probably on the boring side or on the slow side, if anything. We'll take it easy in the beginning. I'll look very much at the hardware side of things and introduce you to that, to the photonics hardware, which I don't think you have heard about at this conference or this summer school here yet. And I will tell you something about the pros and the cons, maybe, of how you want to build technology based on photons. So, quantum complexity, you're all experts in this. So on the photonic side, it's really very simple. If I have a magic source of photons that just boom, 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 emits a single photon on demand, then I can produce an immense quantum complexity, because those are qubits of information. I encode a qubit by just giving the photon two opportunities, going up or down on a beam splitter, and that's a qubit of information that I'm deterministically encoding into the photon like that. And of course, we all know that the amount of information in these n qubits, that grows exponentially to the nth power. That's so the exponential explosion, that is kind of the complexity that is behind quantum physics, but also pertains to the resource, of course, why we want to build quantum computers in the end. And entanglement, you're also all familiar with entanglement, of course, that this fellow didn't really like. You could have a source that emits pairs of photons, you send them off to two different directions, you give them two opportunities going up and down. They go up and down at the same time, but they are correlated with each other, so that if you measure one of the photons, and photons travel fast, so you could send it across the internet to the other side of the globe and do a measurement on this photon there, and the other photon back in Copenhagen would immediately be influenced by the measurement. So we are locally connected by entanglement. So that's kind of the resources that we're interested in generating in the lab. And I will tell you about what it is I've been drawing here, how these on-demand single photon sources and entanglement sources work, also some of the specs of those sources. And I'll tell you something about also the applications that we foresee. So photonic quantum technology, pros and cons. Why would you build a quantum computer, for instance, based on light? Computers based on electrons, so that sounds like a really strange thing to try to build a computer based on light. So would there be any arguments for? Well, yes, there are some, and some of them are listed here. And I think a very important one is that when we do quantum optics, when I teach quantum optics, textbook quantum optics, there's no temperature in the equations. So photonics is a zero temperature theory. I don't care about temperature. I don't need to introduce a temperature. Why is that? That's because the electronic energy, the photonic energy is so large that any thermal fluctuations, it's really your Boltzmann factors that kills the thermal photons. They don't influence my photons at optical frequencies. So I do not have stochastic noise of photons. Photons can just travel. A photon can come from the star and still be polarized. So I have qubit information encoded in a photon and can send it over long, long distances. There's no stochastic noise. That's a very, very nice thing because, of course, all other systems, I mean, they will be sitting and decohering due to the environment. Okay, what else? Well, there's quite some technology that you can piggyback on in photonics. So there's advanced photonic integrated circuit technology. I've illustrated an illustration of how an advanced circuit could look like. This is over here. This technology has been developed over the years for the telecom industry. So there's really technology available that can start to encode information in many photons. So you can couple many photonics. You can route photons with very high fidelity. And you're piggybacking on this technology that has already been developed. And well, then we start to develop also high-quality photonic sources, as I will be talking about here. So this starts to come along because you can say, yeah, all this is great. Photons do not experience stochastic noise, but if we cannot generate the photons, do I care? And indeed, we start to be able to generate these photonic sources with very, very good metrics. So what are the cons? Well, as we all know, photons do not naturally interact deterministically with each other. Two qubit gates between two photons. Doing that deterministically, that's just very hard. It's not impossible, but it's really hard. Photons interfere with each other. That means I can have probabilistic gates, but if I want them just deterministically to do a two qubit operation, this is really hard. And then the real challenge with all photonics is really loss. Photons get lost. I send fiber, it may not come to the other end, may not arrive over in the US where I tried to send the photon to. So photonic loss is the name of the game actually for how we are going to scale all this up, which is also nice in a sense because this is a very, very classical hardcore engineering thing. It's about how good devices can I make. It's about fabrication, imperfections, tolerances. It's about coupling losses. It's about, really, really, brute force engineering challenges. That is something that you can do something about and you can work on. So a challenge accepted. I think there are these challenges here, but there are also some stuff to work on, and I will say something about this as well. And please interrupt me when there are questions. Okay, so the first part I was intending to speak about is about these single photon sources, these deterministic photonic sources, the figures of merits and their performance. So how do we create a single photon? So maybe that was 100 years ago that our founding father, Niels Bohr, explained the Bohr atomic model that you have all learned about at school, and the electron emits a photon when it decays from an excited state to a lower lying state. That's how a single quantum of light, a photon, is born. But the photon is, of course, emitted in all different directions, so this is not a deterministic source. I need to collect the photons, and I need to control its direction and also the emission time. And this is what we can do today when we start to embed these emitters, atoms, quantum dots, other emitters, inside photonic nanostructures. So we're using modern nanophotonics technology to control the light emission, essentially. So one of the tools you can work with is called the photonic bandgap structure. It's like a semiconductor for light, proposed back in the mid-'80s by Ilya Jablonowicz. that if I take a periodic arrangement of holes in a high refractive index material, for instance, like this, then I can create a band gap so that you have destructive interference. You put an atom inside this photonic band gap structure, and you can, if you do it right, you make the right structure, and you have sufficiently high refractive index contrast in this medium, you can have destructive interference along all directions. So the atoms want to emit photons in any directions, but you have destructive interference no matter what direction this atom is looking. So it cannot emit the photon. I can suppress spontaneous emission, and it can inhibit spontaneous emission inside such photonic band gap structures. So this is also called the Purcell effect, that you control by putting the atom inside a structure. You control the emission properties. You get it to, in this case, not to decay at all. So a photon cannot be emitted. How does the atom know that it's sitting inside a photonic crystal and it cannot emit a photon? Well, it has one interpretation is that what we do is that we are modifying the quantum vacuum fluctuations that is driving spontaneous emission and gets the atom to decay. Here I'm shutting off these vacuum fluctuations, and the atom cannot emit a photon at all. So this was turning off the light in a clever and expensive way. I could have not turned on the light. That would be an easier way of, instead of turning off the photon emission like that. So here comes the trick. Now I'm leaving out a row of holes in such a photonic band gap structure. That creates a photonic crystal waveguide, and now I have this emitter. It's a quantum dot that we're working on, sitting inside the structure. It cannot emit in all the different directions here because of photonic band gap, but I gave it one direction along which it can emit. That's this defect direction where I left out a row of holes from the perfect photonic crystal structure. So that's our deterministic photon source. Instead of using atoms, what we are working on is quantum dots. So quantum dots consist of thousands of atoms, tens of thousands of atoms, but have optical properties like single atoms. So you have, it's semiconductor physics, so you have band structures, but you're embedding a small, a material, indium arsenide, with a small band gap inside another material, gallium arsenide, with a larger band gap that generates an energy well potential where you're trapping electrons and holes. And I can have a single electron-hole pair that is called an exciton that recombines and sends out a photon. So you can think of this as a solid-state atom, also sometimes called an artificial atom, where we have some control, because here we can start to grow these quantum dots with precise properties, and thereby also control its emission wavelengths, for instance, by controlling the size, by the size confinement effect. The other nice thing about quantum dots is really that, well, they are solids, and so that means I don't need to laser trap and cool the atoms and get hold of it first before I can start doing my experiments. The quantum dot's just sitting there in a substrate, and I can make the photonic nanostructure around it, like what you're seeing here. So we make structures like this. We are punching holes. With the distance between the holes here would be a few hundred nanometers. Why a few hundred nanometers? That's because that's a wavelength of the light, half a wavelength. That's a Bragg diffraction condition that you need to fulfill to create a photonic band gap. We make a membrane, so you see that what is underneath here is actually air, so we're etching away the semiconductor material below the quantum dots, and there's also air on top. And why we're doing that, that's because a third dimension that I didn't tell you anything about. There's of course a third dimension. The photon could just fly out along the vertical direction here. But this is actually suppressed very, very strongly in these structures here also, because you have total internal reflection between the high refractive index material of gallium arsenide, has refractive index 3.5, and the surrounding material, that is air in this case, that has refractive index 1. So we get three-dimensional confinement of light in a two-dimensional photonic band gap structure. And we can nice and conveniently come from the top and do experiments on this platform by restricting to a two-dimensional structure. So that's why we are working, that's why the devices look like that. So the physics I'll be telling you about, that's really very much the core of this interface here, this light-matter interface, this single photon source, but more generally light-matter interface, as I will be emphasizing. It's not the only way to get deterministic single photon sources. And in particular, my colleague Richard Warburton here in Basel is doing absolutely brilliant work, and we are very, very closely collaborating, Richard, Arne Ludwig in Bochum and myself, and our groups, on this kind of physics and technology. So Richard is using a cavity structure, as you see indicated here. It's a vertical structure where he puts a mirror, an external mirror. That's what is drawn up here. He has a quantum dot sitting here, and then you have an internal mirror inside your semiconductor material, and then you're creating a small cavity resonance between those two mirrors here. So he's enhancing, you could say, a specific mode a lot to get strong photon emitter coupling, where you can say we are suppressing the coupling to all the unwanted modes. It's two different ways of realizing some of the same physics, or exactly the same physics. Okay, so what's a little bit more details, experimental details maybe. I don't have a good feeling for how much experiment you want and how much theory. It's a little bit of both. So a few experimental details on this platform here about the operational principle of these deterministic single photon sources. So here it is again. Here's setting a quantum dot. Here's a defect photonic crystal waveguide mode. And how we're operating these sources is that we come in with a laser from the top here. So they're sending in pulses, repetitive pulses, to excite the quantum dot to do pulsed resonant excitation. And then a key point is because that's, of course, the drawback of solid-state systems that I didn't mention, that solid-state systems are dirty. You know, I said, oh, fantastic, I have a quantum dot, it's sitting in a solid. Isn't that great? I don't need to laser cool and trap it. Yes, that sounds great. But sitting in a solid also means that there's maybe charges roaming around. There may be vibrational phonon modes. There's all kinds of solid-state jazz and reservoirs, if we want to say with physics terms. There are open reservoirs there that my quantum dot system is coupling to. So it's a much more advanced system than if I have a two-level atom laser trapped and cooled. There's really nothing that's not much that disturbs the atom. So I have to care a lot about all these reservoirs. I have to prove at all that I can get into a regime where this behaves quantum mechanically. Many systems do not behave quantum mechanically. I need to be able to shield my little quantum dot sufficiently well. And there it turns out that there's a lot of details in these electrical contacts that you can put on these structures. So these are semiconductor materials. It's heterostructures, so PIN, heterostructures, where you can, with very high precision, grow high-quality materials, and of doped materials in these semiconductor membranes, you can put high-quality electrical contacts on to really sweep away carriers, clean up the electronic noise environment of the quantum dot. And this is a very, very non-real thing of this platform, that this works so well. It could not have worked, but that's really some progress here. These are more technical points of that on this platform you can spatially extend excitation and collection. So you see I'm exciting the quantum dot at one spatial position and actually collecting the photons from a grating. This is an outcoupling grating that we have specifically designed here to couple the photons out. So that means I don't need to do any polarization tricks of filtering and so on. I can actually, collect every single photon. I don't lose anything in my spatial extension. So that's the advantage of this specific platform. And that you can separate the excitation spot from the collection spot in ways as indicated here. Yes? How do I do that?
Yeah, so you have this laser.
Yes.
You have this thing that is coupled to the laser, but it's way more strongly coupled to the mode.
Yes.
So why does this maybe can you explain it?
Yes. So how I'm exciting through some weak radiation modes here. So you should think of this quantum dot can emit to the waveguide, but it will also have a little bit of leakage out here. And that's exactly what I'm exciting through these leaky modes here. And I have a lot of power here, so I can just crank up the power and excite through them. And then that doesn't couple to the guided mode here, at least not much. There will always be a little bit of crosstalk between the different channels. But this excitation channel here is not strongly coupled to the actual mode that I collect the photons. So that's how I separate those two.
And this is achieved by choosing appropriate polarization?
Yeah. So indeed, so here you're controlling, here you're aligning and controlling the polarization of the incoupling light, exactly. So that's what you're tuning here, tweaking here, in order to not get leakage laser light in your outcoupling grating. It's key, indeed, so that the excitation wavelength here is the same. It's exact resonant excitation. You're hitting this quantum dot exactly on resonance. So that's a very important point, how to filter away excess laser from the actual photons that are being generated. And that's what I was just explaining. Yes, so here's some typical result of, we do a pi pulse coherent resonant excitation, and you see a 10 megahertz photons generated, in this case, into an octave and so on. I think this works pretty well now. I think I'll skip this, but this is really details about these PIN heterostructures, what that enables in terms of charge noise control that I already explained, but it also gives you some opportunities of doing spin physics in these systems. I'll return to spin physics later, depending on how much time we have. Okay, so what are the figures of merit? So you can say, so how well does this work? What are the important figures of merit? One important figure of merit is what we call the beta factor. That's simply the coupling efficiency. What's the probability that once I excite the quantum dot with a pi pulse here, I actually get a photon in a single propagating mode in a waveguide, and I can collect this photon. And it turns out that this number is really high. This is actually a number we worked more than 10 years on to really nail. This is an experimental lower bound of 98.4%. Yeah, there's a long story. Sometimes when you have a number that is close to 100%, it's not really easy to measure it and being sure that it's so high. So we have been nerds, and we have been obsessed about beta factors and putting experimental, solid, for sure bounds on these beta factors. And you can say, why on earth have you been obsessed about this number? Because is it important how many photons you can collect? Because I bet when you want to couple these photons off chip into a fiber or whatever, you lose a hell of a lot of photons and detect the photons and so on. And you are absolutely right. This is so the question I'm posing here is does the beta factor, loss eventually in your, do you need to be obsessed about that you can collect them with such an exceedingly high efficiency? Because if something else in your chain is lossy, maybe it would be fine to have 95 or whatever. And this is a rhetoric question, so I wouldn't pose it if I didn't think that this was an important question. I think this figure of merit is tremendously important, because this is not the figure of merit only that determines how many photons can I generate, and then also eventually how many photons could I deliver to my customer. I'll say something about a startup company later that actually has customers. It's not just that figure of merit that this beta factor is. The beta factor is a figure of merit of how deterministically I can interface a single matter qubit, a single quantum entity of matter, so a single quantum emitter, and a single photon. It's a light matter figure of merit. It's not just an efficiency of a single photon source. And if you want to be more quantitative about that, we speak about the quantum cooperativity, that is beta divided by 1 minus beta. That's a figure of merit that goes into also more advanced applications of this interface when I want to do quantum gates based on that, and multi-photon entanglement generation and whatnot. Then it's the quantum cooperativity that would be your figure of merit. And then you can see it matters if beta becomes very close to 1, because you have 1 minus beta down there in the numerator, so the cooperativity would really beef up if beta gets close to 1. So what we are producing here with that stuff is not just this dumb source of single photons, that it's at a fundamental level a light matter interface. And for that reason also, I mean, I think it has more general importance. It's not only a single photon source, it's really also, I mean, quantum gates and spin photon interfaces and maybe even interfacing superconducting qubits and spin qubits to photons and whatnot, because this is a fundamental light-matter interface that we are working with. So this formula is nice and simple. It's also totally wrong unless I have a perfect two-level emitter. Any decoherence processes, any broadening processes will reduce this quantum coercitivity. So this simple formula only holds if I have a perfect transform-limited quantum dot emitter line inside the photonic nanostructure, not broadened by phonons, nuclear spin noise, charge noise, your own favorite noise. Any noise processes, of course, will broaden. And again, this is why I'm excited about this platform. I've worked on this platform for more than 15 years. I've been excited all the way through, but I've become more and more excited because we solved these problems. We have transform limited emission lines in these structures now. It actually starts to become quantum. Maybe it was nanophotonics for the first 10 years where everything was broadened by all kinds of noise processes. It's fine to do nanophotonics, but you need to, really get to the core of that and be able to reduce it in order to make it quantum. And I should emphasize again that Richard Warburton has really been decisive in enabling that advancement on this plan. Yeah. So what are the figures of merit for the single photon source? Well, one obvious figure of merit is the source purity. That's simply I take these pulses generated from my quantum dot source, and I'm asking what's the probability to have one and only one photon. I gauge that in what's called Hanbury-Brown twist experiment. I take a beam splitter and two detectors, and I do coincidence measurements between those two detectors. And if they never click at the same time, then I know they have one and only one photon coming. If they click a little bit, once in a while, at the same time, that's the purity of the source. What we call the purity. There's some different terminologies in different fields that sometimes confuses people. This is not the purity has anything to do with the coherence of the state. It's only about the multiphoton component in the pulses. And here you can see some of the results of such Hanbury-Brown twist measurements, and you see the center peak here is really, really strongly suppressed, and we at least have 99% single photon generation. And also importantly, if you're then looking at long-term correlations in these correlation traces here, G2 as a function of tau over long time scales. Okay, so what are the time scales? What are all these pulses? That's because I'm exciting the quantum dot every 13 nanoseconds. So the photons comes every 13 nanoseconds. That's what these peaks here means. And I look at when do I have coincidence events at the same time, and hardly ever. But then I also look for correlations on longer time scales out to hundreds of microseconds here, and see that these peaks here do not decay. So any blinking processes, any noise processes would mean that these you would see a decay of these correlations on longer time scales. So it's actually very important to observe that this is not the case, that you don't have blinking going on in your emitter. Yes? Blinking would be, for instance, that the quantum dot emits photons, but then your exciton becomes trapped somewhere and the quantum dot goes dark, for instance. So there's a very common phenomenon that happens all the time, unless you are having these electrical gates very, very well under control. So again, there's charges everywhere in the semiconductor. You can trap defect sites and so carriers. So that's really important to see that here under these experimental conditions, we don't see any blinking. The quantum dot continues to emit photons measured out to 100 microseconds. And it emits every 10 nanoseconds a photon, so 100 microseconds, 10 nanoseconds, so that's 4 orders of magnitude, 10 to the 4 photons being produced without the quantum dot going dark. So you can see a massive resource generated just by one quantum dot, a massive photonic resource. What's the coherence? So there you do a Hongwu mental experiment. You start to interfere photons with each other. You do that in an experimental setup like that, an unbalanced Mach center interferometer. You take a beam splitter, with a long arm and a short arm, and then you in that manner interfere consecutively emitted photons from the quantum dot. I see it here, right? It emits these trains of photons, and by sticking in a variable delays here, I can interfere photon 1 and photon 2, or photon 1 and photon 3, or photon 1 and photon, well, out to photon 115 we have tested experimentally here. And again, if the photons are totally indistinguishable, so that meaning that we can encode very good qubits in these photons, then they will interfere with each other. That means they will bunch so that one photon in, one photon in. Either 2 photons will go to that detector or 2 photons will go to that detector. I'll generate 2 0 plus 0 2. No coincidence events between those 2 detectors, so I'll never have 1 1. I do a little bit, and this little bit tells me about the indistinguishability about the photons. So that's what we're extracting here from measurements like that. You're making them distinguishable by rotating the polarization here, or you're making them indistinguishable. You're comparing those 2 data sets to each other, and from that you can get the photon indistinguishability, what is plotted here. And the number is larger than 96%, up to 98% we are seeing. And again, importantly, remains unchanged out in the string. So here we measured photon 1 and photon 115 being as indistinguishable as photon 1 and photon 2. So what that means is that this source just produces a huge string of high-quality photonic qubits, and they're just there. Go ahead, use them, and I'll tell you about how that works in practice. Yes?
Where does the distinct photons come from? Is it like frequency distinguishability or polarization? Or
Yeah, no, yes. So indeed, so here I make them distinguishable by rotating the polarization here.
Yeah, but even when they are indistinguishable, this 4%.
Where does the 4% come from? Yes, excellent question. So the 4% comes from phonon broadening, actually. It's actually down to the 2%. We have 98% now. So we fully understand also these numbers here. So there's residual broadening due to phonon processes. Our experiments at a few Kelvin, but even at a few Kelvin, so the emission spectrum of a quantum dot will have a 0 phonon line, and it will have some a little bit broad side bands. These side bands we don't care about, we filter away, that's 5% in them. And I'm interested in what is the broadening of this 0 phonon line. And even at 2 Kelvin, there's a little residual broadening of this 0 phonon line. And that's exactly what gives this 98%. And you could say, maybe I want 99%. Do you have a way to get to 99 and 99.5? And actually we do, exactly because we know exactly what phonon broadening processes, or what phonon modes in the membranes gives rise to that. That also means you can start to do something about it. We actually even have patents on this, on how you could take that to 99.5 by doing some clever clamping tricks of the structures to overcome this. So my claim would be, the physics is understood here. There's no, it took a long time, but we have a model and tested this model, and we understand the physics. It's really engineering, and it's to take that further. And then it's about, what do I need, or what do you need? I mean, do you 98, is it good enough? 99, 99.5? Well, that depends on the application, of course, what you want to do with that. And this is also what we are really putting a lot of effort into, because for us hardware people, there's a risk to get in love with your spec. You say, it's very important to have highly indistinguishable photons. Yeah, well, sure, but how highly indistinguishable? And well, it depends on your application, depends what you want to do with that. And maybe it's not useful if another spec is down the drain. And I think that exactly these kind of studies, we and I'll say something about it if I get to it, put a lot of effort into these kind of benchmarking. Very much depends on your application. I don't think indistinguishability is a key thing anymore. It's good enough for many things. I think it's a loss. That is, but it's an excellent question.
So you have to look at cryo temperatures.
Say again?
You're working with cryostats.
You were working with cryostats. So this is a few Kelvin temperature, and that's important. And you can say cool it down to 100 millikelvin or 10 millikelvin. We could do that. It wouldn't be much better than so you actually have to do some phonon control stuff if you want to go much higher. Can be done. Yes, so, okay, how do we couple the photons out? Losses, everything. I won't say much about this. This is really an engineering thing. We can make these tailored gratings, make them with E-beam lithography. You have DBR mirrors inside the substrate so that you don't just lose half of the light down into the substrate. Well, we've demonstrated 90% coupling efficiency from one of these chips here, devices, and into an optical fiber. Good enough, certainly good enough for our physics experiments and for physics lab. Of course, if you're talking about technology, then it's about loss tolerant encoding for, again, depends on your application, but if it's a quantum computer, then it's really about your making loss tolerant encoding and look at the whole chain of losses in your device, in your architecture, and there I think you really have to work hard. There's nothing in physics that prevents us from taking these numbers much higher. 99% evanescent coupling from chips to tapered fibers, for instance, has been demonstrated with at least 97% efficiency. So again, hardcore engineering if you really want to make this work. Okay. So line width of the emitter, I think I mentioned it already. All these broadening processes, and you care about them. I showed you that photon 1 and photon 115 were as indistinguishable as photon 1 and photon 2. How long time did it take to produce 115 photons? 800 nanoseconds. So that means that there's no drift going on the 800 nanosecond time scale. Perfect. And the residual broadening was this high, fast phonon decoding processes that you were asking about. What about if I look at longer time scales? I can do that, for instance, by measuring the line width of the emitter. You do that in a transmission experiment. You have the quantum dot and a nanostructure waveguide here. You have input and output gratings, and you simply just take a laser, CW laser, send it and through the waveguide and look at the extinction dips here when you're hitting a narrow line with quantum dot and measuring the width of that. And here you are probing your sensitive. I mean, these measurements are millisecond timescales, so here you're sensitive to all broadening processes on up to millisecond timescales, and we're observing down to 15% residual broadening above the natural line width, meaning that you really overcome all these noise processes to a very, very large extent that I was talking about, where we are comparing the line width here to the actual decay time when we are doing a time result measurement. So that just emphasizes that these heterostructures, these electrical contacts, all this noise cleaning job that we have been working on the dirty solid-state platform actually starts to work pretty well. Okay, so let's just see how much do I have here. Yeah, I think I'll just take a few more and then we can take a break and then get to some more advanced stuff. The point I want to make now is that I've essentially told you how to produce an on-demand source of single photons, right? You have this source that emits photons that comes like pearl on a string, and there's a massive resource, 115 photons. Maybe there's even millions of photons because in a millisecond timescale I can emit 1 million photons. So just one quantum dot emits a huge resource of photons of a very high quality. So perfect. So now I have everything I need. I maybe need 1 million photons to build a quantum computer or something. So just one quantum dot produces it, doesn't it? All I have to do is to route these photons, right? Because I have them one at a time. They come as pearls on the string, but I would like to interface them and interfere them with each other. So I need to have them at the same time. But that's simple in principle. I just route the photons. I just make a cascaded network of chips, like indicated, of what do I call it, chips of switches, sorry. I make a cascaded network of switches where I route the first photon into one waveguide, the second photon into another waveguide, and so on, so that I can end up, this illustration shows you how to send 4 photons into 4 different modes by using 3 different switches. And I know when the photons come, they're triggered by the excitation pulses from my laser. So I just stick in an optical fiber delay to convert one deterministic source to 4 deterministic sources at the same time. Nice and simple. But of course, challenge is loss. How would I do that? How can I do low loss switching here? How can I couple all these fiber coupling steps here? Will be lossy. There will be losses in the fibers also, absorption loss in the fiber. So it's really mundane engineering of making a demultiplex source by scaling up like this. In reality, we don't do it like this. That's just a conceptual figure. You don't want to have n fiber coupling stages like this. You want to have just one of them, because and you can do that. Maybe you want to do today much of it in bulk optics, as you see this proof of concept experiment from the Chinese group, Jian Weipan, Xiaoying Lu, where actually the 20 photon multiplexing experiment with electro-optical modulators on an optical table. But the more of that you can do integrated, as indicated in this figure here, of course, the better. Okay, so this is not the end of the world. So this is not, you need more resources, and I'll get to that in the second lecture about how would we build something more advanced, because losses kick in exponentially here. So if I'm asking what's the probability to generate n photons, that scales as my total transmission efficiency to the nth power. So this loss fight here is really a tough battle against an exponential blowing up enemy that you are having. But you could start to benchmark the specs, and you could ask the question, so what would it require to do a quantum advantage experiment, for instance? It's just a very quantitative benchmark. Quantum advantage meaning that's also used in different terminologies, but I use it here in what Google calls the supremacy argument, that can I do an algorithm with my resource in the lab so that world's most powerful supercomputer cannot calculate anymore what my hardware in the lab is doing. With photons, that would be to do boson sampling algorithm, where you are interfering the photons with linear optics and sampling from that collection of photons. And you can benchmark the performance of your hardware to say, is the indistinguishability, for instance, good enough to enable such a quantum advances experiment? And that's exactly what we have done, and that's what you see the results of here. So here you see a calculation of the of what we'll get if we do boson sampling with that resources from a quantum dot with the indistinguishability of 96% reaching out to 115 photons that I was just talking about. So here's calculating the variational distance as a function of number of photons from what you would get with an ideal boson sampling without any imperfection. So it's really how close do you get to the real result with your implementations, with your real hardware in the lab. And you see that the quantum advantage regime would be above 55 or so photons, and the classical computers cannot keep up anymore. So that would be the quantum advantage regime. And you see that for our source, when you put in the numbers, 96% indistinguishability, the G2 and so on, 99%, you see that you'll get a variational distance that is not decayed all the way to 0. So you're actually able to get meaningful performance out in the quantum advantage regime with that kind of metrics of the source that we have demonstrated in the lab. And we benchmark to actually the experiment in China, where they have a faster decay, and this is actually because in their experiments you're not seeing this solid, rocket solid indistinguishability out of the chain that I was explaining, out to 150 photons. You'll have a decay in the indistinguishability because you will have some noise in your device, and these things can be really detrimental to the applicability of your source. So it's really fine prints of your sources that you need to look at if you want to take it into this regime. And then you can say how efficient should it then be to that I can run on this source a boson sampling algorithm in a foreseeable amount of time that we have also estimated here. So if I say I want to run for 30 days, that's within capabilities of a lab experiments, I should be able to produce photons with 78% efficiency into an optical fiber. And then you could actually plug this source into the experiment in China that I mentioned and do a boson sampling quantum advantage demonstration with that performance. And this is within the specs of what we can do. Okay. I'll finish off with this. Just say for a little courtesy here that we also started a company, or I started a company already some time ago. It's called Sparrow Quantum. We started in 2015, so back in the days where quantum startups were not as mainstream and popular as they are today. So, you know, when I at a conference was talking about I started this company, then my colleagues would say, you're crazy, and there's no market, and there's no technology, and this is blah, blah, blah. And now they all have startup companies and say, oh, it's fantastic, and, you know, it's a great market, and, you know, it's really exciting, interesting for me to see how this perception, this hype, this quantum has changed quite dramatically over the years. And now we all agree that this is going to revolutionize the world. And so fantastic. You can say, why would I care to start a company? And maybe I can always mention it, but maybe can inspire young people also, because it wasn't in the cards that I started a company. I was not a quantum physicist, didn't start to do quantum physics to start companies and talk to venture capitalists and whatnot. I was there because I liked physics and wanted to understand quantum, and that sounded cool and difficult. But I must say it's actually very exciting and has been very rewarding to do that for two different reasons. One reason is that, you know, it's no bullshit in the sense that, you know, if you're getting older, you have no idea how many introductory paragraphs I've written, and where I say, oh yeah, this may be useful for a quantum computer and a quantum internet and so on, and written many of these nice introductions and a great sentence, and maybe we can convince the referees and the editor with such a great sentence. And then sometimes you should ask yourself, yes, what you wrote there is a great sentence, Peter, but does it have anything to do with the reality? You know, is this actually potentially an enabling building block for a quantum internet or a quantum computer? Is it? and you can say, well, you can decide not to try to embrace and encounter this question any further, or you can say, well, maybe. And I think for me this has been a little attempt to, you know, if there's some value to what we're doing, it's a real value, if I really believe in it, then this is something that you could do. You could put it out there, you could mature it, you could see if some other groups would like to buy it and use it, and it's a technology, no bullshit technology ambition to say maybe there is something in this quantum dot stuff there that is worth taking to the next level. That has been one very, very strong incentive to me, that I actually do think that there's some potential here. Maybe that 10 years from now turned out that there was something we had overlooked, doesn't go all the way, but I see a potential and an excitement to follow this potential. The other is that it's actually you're starting to engage with many more people. So I like to speak to quantum nerds like myself, but it's also actually nice to suddenly, you know, get your world becomes bigger and you get new challenges and new things, and the company is really introducing you to new challenges and new people, and some of them are also as crazy, but crazy in a different way than we are. Okay, so we started in 2015. We had quite a lot of research already, 10 years of research, to get to the level where we see some of the child diseases have been cured. And I think that's important, that you need something, at least if you do hardware, you need something where you know what is going on. There's no quick, this is a cool system, and maybe it could be room temperature on the others, and then you just jump at it. That can be quite difficult if you don't really know the ins and outs of your platform. And then, then there's a long story here, and getting the right people into the company and whatnot. And let's not dwell into this. This is a product roadmap of Sparrow Quantum, as the company is called. And it's a very commercial roadmap. The single photon chip that I spoke mostly about is about packaging it, making it accessible to the customer. It's about fiber coupling the chips directly so that you can get a fiber coupled single photon chip. It's about cryo integration, so integrating the system or the chip into a cryostat. It's about getting the cost price down for the customer, easy to use, things like that. And then it's also about taking this technology to the telecom wavelengths. So far we're working at 930 nanometer. And Sparrow is dreaming about being the provider of sources, on-demand single photon sources to the customers that may want to build an advanced processor. It could be PsiQuantum, building a quantum processor with photonics, and maybe Sparrow can develop these photons very, very resource efficient. And and then we take a break with showing one of the commercial videos here showing the technology. So here you see the pulse laser that excites the quantum. You have these electrical contacts that are cleaning up the environment. That's key that I talked about. Photon is emitted with very high efficiency into the photonic crystal waveguide, and then it's routed out through other waveguides here. You don't want a long photonic crystal waveguide. They're lossy, so you couple them out to normal waveguides and out through these specially engineered gratings out to the customer that is sitting out here waiting for the photon to come. So I suggest we take a break now, and then it will be about entanglement sources after the break. being emitted in the late time bin. And this, whether it's in the early or the late time bin, that's correlated or entangled with the spin pointing either up or down. And the nice thing is here, I can just repeat this. We're very good at repeating that in photonics. I can just excite this quantum dot many times and emit, excite, and I could, in principle, produce a long entangled state where the quantum dot spin is entangled with all the subsequently emitted photons. So they come out as pearls on a string, but now these these pearls are entangled by the spin. And ultimately, you will produce this. This is the end photon GHC state. If the spin was up, then first photon was emitted in the early time bin, second photon in the early time bin, third photon in the early time bin, so on. And vice late time bin if the spin was pointing down. That's an NGHC. So it sounds nice and easy. And I talked about millions of photons being emitted by a single quantum dot. So you may dream about that maybe have 1 million entangled photons on demand here emitted by the quantum dot. But unfortunately, things are a little bit more complicated. So we introduce a spin. That's another new reservoir. That's new decoherence processes. You have to care about how does this spin couple to the nuclear spin bath. How long does it live? Not very long. And that is one of the reasons that maybe this platform says this is absolutely a useless platform. What is your T2 star? I barely dare to say it. My T2 star is 20 nanoseconds or so for spin in this ground state here. 20 nanoseconds, my goodness. This is probably totally useless for anything. It's one of my famous rhetoric questions. I wouldn't say it if the answer was yes, it's useless and sorry, and end of talk. No, because we have a tool here, so I can live with a short memory, 20 nanosecond memory, because I can produce these photons so exceedingly fast. I produce these photons at like 100 picosecond rate. So even within 100 picoseconds, you know, the spin is coherent, and actually T2 star for this particular entanglement generation is not the key infidelity, and I'll break down the infidelities for you in a second. It's not the T2 star. It's because all I care about is the T2 star within the time it takes to emit a photon in this specific protocol. So I worked around my Achilles heel of the platform, which is this ridiculously low T2 star. By taking advantage of that, I can generate these photons exceedingly fast. Okay? So here's a breakdown together with Anders Sørensen's people of really looking hard into our platform here and all the infidelity contributions in the real experiment and how good could this possibly be. And there are a number of processes, of course. There's indistinguishability of the photons. That's this phonon decoherence process we talked about already in the single photon emission. That's a contribution. There is a fourth level that you now, let's see. So you have a 4-level scheme and you're exciting, emitting on this transition here. You don't want to excite this 4th level here. That will give a wrong photon. But if it's not sufficiently far detuned, you will get a little contribution from that. And then there's actually something that we call the branching ratio of the emission on this transition here that I use to excite and emit, compared to that the photon is decaying on the cross transition here to produce a photon over here. And you want this branching ratio here to be large. And it turns out that the photonic crystal waveguide introduces an asymmetry for free so that you actually get a branching ratio that is reasonably high. And that's a long story here of really going deeply into all your errors and mechanisms in this specific protocol that we have optimized in order to do as good as possible with the hardware that we have available. And you see that you can get down to 1.6% error per photon when you are putting in real numbers for these error contributions here. And this is actually starting to approach the threshold for being able to do fault-tolerant quantum computing. So at least we are getting into the right regime, which is again, non-trivial. It could be that the fundamental limit would be 10% because of whatever branching ratio or indistinguishability or whatnot. So you really have to look deep into these numbers here. 1.6% error per photons, that means the infidelity as the number of photons grows more or less linearly. So if I produce 10 photons or so, we have 16% infidelity. So what you would instead do is to produce small clusters, 5 photons, cut them off, produce another 5 photons, 5 photons, 5 photons, and fuse them together with linear optics. Okay, so this is just relatively fresh experiment. I don't think I will drag you through the details of how it actually, what we have achieved in the lab, of where we do this experiment with a whole spin, driving these transitions. We get very good indistinguishability. We don't get fantastic entanglement fidelity yet. I promised you 1.6% error, and I have 33% error. So we are not there yet. In Anders' theory, there was an infidelity that was not included yet, and turns out that this is how good we are to do the actual spin rotations. So the spin rotations, we do that optically, and it turns out that you're introducing your decoherent in these spin rotations, and this is actually what limits our entanglement fidelity. We believe we have tools available to fix that additional infidelity so that you can do spin rotations with high fidelity. If not, it's simply not a good idea what I'm proposing here. Yes?
What's the limitation? Is it your laser that you drive the quantum dot?
Yes. Maybe I will explain you a little bit more. So how we do the spin rotations here is to drive a Raman transition over here. So it's an optical rotation because we have to do it pretty fast. And it actually, and we use quite a lot of power to do these rotations because we come from the top also there and do these rotations. And that's simply because of these weak radiation modes we're coupling through. We're actually dissipating a lot of power. And that turns out to give an additional spin flip rate on this transition here. When we measure without these spin rotation pulses, it's much longer, but when we do the spin rotation pulses, the T1, there's a T1 component on spin here that is shorter, and that reduces the spin rotation fidelity to 90%. And that is what limits the entanglement fidelity, because we do a lot of spin rotations. For each photon being emitted, we actually do 2 spin rotations. So they're quite costly. So doing that with 90% fidelity is not good enough. In the literature, this has been done with 99, and we hope that be able to fix that, and that would immediately scale up our entanglement source. But that's what limits right now. One thing I didn't emphasize here is also the flexibility here. So I told you how to produce a GHZ state, but I could also produce a one-dimensional cluster state. That's really depending on what spin rotations I'm doing on the quantum dot. Whether I'm doing, this is a pi pulse here, but I could do either pi or pi over 2 pulse as a last spin rotation pulse. And for that from that, I would produce either GHZ or 1D cluster state. And you can also do other type of cluster states where they're not like a string. You can also get some other entanglement topology or structure, really depending on how you apply these spin rotations, in what order you're applying these spin rotations with your arbitrary wavefront generator, essentially. So there's some flexibility here in entanglement production that is quite handy. Okay, so that's the experiment right now. Still in progress, and we hope to do this much better. Now I want to say something about what is next. So far I spoke about one quantum dot emitting photons in entangled states and possibly many entangled photons. And I think it's important to say that I had this question in the break also. I think Our platform is a platform that is very good at emitting many photons, so all applications should kind of make use of that, because that's what is relatively cheap. It doesn't mean that we cannot take additional quantum dots, and this is an example where we'll take 2 quantum dots, going from 1 to 2 quantum dots, what that enables, quite a lot. But that's kind of our building, our scaling up. We don't want to take 1,000 quantum dots or 1,000,000 quantum dots, because quantum dots are, unlike atoms, they are slightly different. So you need to compensate their differences locally if you want to tune them really into resonance. And also, even when I start to do experiments on 2 quantum dots, then I'm also sensitive to noise processes on any time scale. Even the slowest drift, even the 1 second drift would matter when I want to couple 2 different with each other. When I take just one and have it emit many photons, then it's only the drift on the time scale that it took me to generate my 1,000,000 photons that matter. Or when I start to take 2, it's drift on any time scale. But of course, very slow drift you can compensate with servo loops and so on. But it's just an additional complexity to be aware of. So few emitters, many photons. That is kind of the guiding principle of how I want to scale up. Taking 2 quantum dots, coupled through a waveguide, for instance, and this is just an image of a structure where we see 2 quantum dots in there. I didn't bring these data, but we have some very exciting results on the way also on coupled quantum dots through these waveguides, where we really start to see entanglement between 2, and it looks very promising. I'll just tell you about what kind of opportunities this enables. So this is a protocol from Sophia Economos group that explains how you could produce entangled states with 2-dimensional entanglement topology from 2 quantum dots emitting photons, where, or actually 1 quantum dot emitting photons, emitting 1D string of cluster states that I explained before, and the other emitter doing gate operation on the emitting photon. So you see you can generate, on the emitting quantum dot, so you can see you can generate a quite elaborate and advanced entanglement structure just from 2 quantum dots emitting, where one emits photons and the other is doing entanglement operations on the emitting quantum dot. So you can produce, for instance, a state like this that is turns out to be very well suited for quantum repeater application. And we also benchmarked in quantum repeaters how you could possibly use this hardware for a quantum repeater architecture, and also how good should that hardware be. And let me say something about that. So one way, or a quantum repeater, I think you know the task is about sending quantum information through lossy systems. You can say the standard quantum repeater architecture, generation 1 quantum repeater architecture, requires a quantum memory, and you are heralding the generation of entanglement between 2 stations here, and you need to keep the information in the quantum memory until you herald. You get entanglement flag generated over here, communicating it back, and you're doing Bell measurements and doing entanglement swapping between different repeater stations like that. That requires a long-lived quantum memory, because you should have this quantum memory alive the time it takes to send the photon and herald the presence of entanglement, and you should also communicate this information back to the quantum memory in order to initiate the Bell measurement. So there's another way of doing quantum repeater, and that's called a one-way quantum repeater architecture. And that works without quantum memories, because as I said, we have a lousy quantum memory on our platform, tens of nanoseconds, maybe 50 nanoseconds, 100 nanoseconds in the best case. So how do you get around that? Well, the idea is that you, instead of relying on a quantum memory, you are sending not 1 photon, so 1 qubit of information. You're sending an entangled state instead. You're encoding a qubit of information non-locally in an entangled state of 50 entangled photons. You send them off to the next repeater station. You lose some of them in the transmission, but the redundancy in the encoding means that I can do error correction on the photons that I receive at the next station. and encode a new graph cluster state and send it off between repeater stations. So this will be extremely fast, of course, because you don't need back and forth communication between the repeater stations. You just send photons and wish them good luck, and then I do measurements on what made it to the next repeater station and encode a new cluster and send it onward and so on. So what we have benchmarked is, so okay, now I want to do that a quantum repeater architecture based on these solid-state photon emitter interface, quantum dots, or also visible vacancy centers like in Michel Lukin's group. But how good should the hardware be? And also, how do I tailor the protocol to what we are good at on our platform, emitting many photons quickly and preferably not too many quantum dots? And this is a specific architecture that we worked out that relies on only 3 quantum dot qubits, or 3 matter qubits per repeater station, not a polynomial number of qubits or whatever, 3, because the less the better for us. Emitting cluster states of about 100 photons, so something we can do within the coherence times that we have in the system. Now I suddenly speak of a microsecond spin coherence time. I told you 100 or 20 nanoseconds, and it's microseconds because we can do spin echo pulses. And I was actually, if you were very careful and paid attention, or an expert, you will actually have seen that in the entanglement generation protocol, there was an echo pulse. There was a pi spin rotation in the excitation emission. And that is a spin echo pulse that actually means that it's not T2 star. That is an important figure of merit. It's actually the T2 time of the spin. The T2 is microseconds. So if you have spin echo built into your system, you can actually, exploit this microsecond coherence time. So in a microsecond coherence time, picosecond emission time, that we worked out that you can produce these entangled states of sufficiently complexity that you can build a quantum repeater based on that. And it requires a quantum cooperativity of about 100, which is also not science fiction for the numbers that I was talking about. So this very difficult, very demanding. It's not something we are building in the lab yet, but not science fiction. I have some building blocks that I could potentially tweak to meet these metrics, and we have tailored this protocol in order to enable that this is something that is within the bounds of what we can possibly do in our system. And then there's the hardest one that you need to do, that you also need to do a gate, a C-sign gate, between the spin and the photon. When these clusters, they come to the next repeater station, I need to do a gate operation between photons and spins with very low error rate, 10 to the minus 3 error. So this is actually the hardest part of this specific protocol that we developed here. But very useful for us hardware people, because then you can really start to bite your teeth into, hey, cooperativity, this is actually good enough. I don't need to be more obsessed about indistinguishability. Fine. I have a gate. There's something there that we really need to develop, and maybe you can be smart about how do you get this less sensitive to errors. Maybe you can get the error rate down on this specific implementation, and you can take it from there. So let me just say a little bit about this C-sign gate operation, how you could possibly do that also with this error rate. And for that, how am I doing on time? Well, you just stop me when you.
Like 25 more minutes.
5 more minutes.
5 to 10. Yes. We started 5 minutes late. So
Okay. Yeah. Let's just see what. It's not too bad. Yeah. I'll tell you something about the C-sign gate, how you could possibly do that, and for that I will introduce something that we call a chiral light matter interaction, a directional single photon emission, some fun little effect that has been developed that you can actually in these photonic nanostructures get photon emission to know the difference between left and right. And it has to do with when you're confining the light transversely in these photonic nanostructures, you get a longitudinal component of the electric field that we usually forget about when we're doing quantum optics. We think of the electric field as being transversely polarized, but actually when you're confining it strongly, you start to get a longitudinal component, and that gives you directionality in the system. So you can have a situation in these photonic crystal waveguides where you have, if you have a sigma plus polarized emitter, then it will emit only to the right, and a sigma minus polarized emitter will emit only to the left. And it has to do with optimizing this D dot E, the polarizations of the electric field in the waveguide to the transition dipole moment of the emitters in a specific way. But the take-home message is here just that you can get sigma plus to emit right and sigma minus to emit to the left, so you can get directional emission, a quantum dot being excited, and it emits only along one direction. So that means now I want to use that not to emit light, but to do gate operations on photons. And I have this chiral coupling, a directional coupling, that I have a quantum dot that can only emit on a sigma plus transition to the right. Now I come and send in a photon here instead, and it scatters off this transition here. The photon can only go forward, so it will also be scattered in the forward direction, and in this process it will require a pi phase shift. So no reflection backward, because this direction is not allowed, only reflection forward, and when you're reflecting on the emitter, you're acquiring a pi phase shift. So what this operation does is a pi phase shift on a photon. A chirally coupled quantum emitter passively does a pi phase shift on the photon. So you could think of taking two of them inside a Mach Center interferometer, sending in a single photon, doing a pi phase shift if the spin was in this direction. So that would be a pi phase shift here, that would be a pi phase shift there. That would lead to a photon being detected in the detector 0. If the two photons of the two quantum dots were in the spin down, there would be a 0 phase shift there, 0 phase shift there. There would be a photon detected in detector 0. So conditioned on a photon being detected in detector 0, that's a parity measurement on the spins. So I'm projecting onto either spin up, up, or spin down, down. If I have one quantum dot spin up, another quantum dot spin down, I would get a pi phase shift on one of them, and that would lead to a photon being detected in one. So optically, by clicking in the detector, I'm doing parity measurements on the spin, and it turns out that so that's a probabilistic process, because I'm scattering photons probabilistically by interacting with the quantum dot. Well, if the beta factor is higher and higher, cooperativity goes out the roof, then I get closer and closer and closer to making that deterministic. I can make it arbitrarily close to unity success probability. That's what this plot here shows. You can actually get infidelities. Again, here Anders and Sahan were working out how robust is this particular gate to infidelities. How good a beta factor should I have? How much detuning can I accept in order to, and how would that influence the infidelity? And you see, you can actually get down, that's my point here, you can get down to this infidelity 10 to the minus 3, 10 to the minus 4 that we were after for the quantum product. Okay, I think I will slowly wrap up. I guess you have a lot of stuff, of course, but I think I'll skip some of this. I'll just say very, very briefly that I've told you about producing photonic resource states, single photons, multiphoton entangled states, and so on. What comes after is, of course, to start to interface, process this quantum information. And there we are relying on these advanced photonic integrated circuits that I was talking about. In particular, lithium niobate photonic integrated circuits is a really, really promising material. We're working with Wolfram Pernis group now at Heidelberg on making these advanced chips where you can tune with gigahertz frequency. You can do operations on these photons, very, very reliable. You can even interface superconducting detectors with near unity detection efficiency on this chip technology, and all this routing stuff, all this processing of the photonics, I would emphasize in particular lithium niobate as a very exciting and promising material. Something we are just starting to do, you can say, in my group, but where we are working, there's lots of activities worldwide, other groups that are really, really experts on things like that has been advancing that. We have been advancing very much the sources, but we are starting to put these things together. For instance, to do photonic simulations, proof of concept photonic simulation, molecular vibrations, for instance, is one thing you could think of really doing in NISC quantum devices here. I mean, we don't do any error correction or anything like that. In the first place, you just produce the photons, you interfere them in advanced lithium niobate platforms, you start to map that onto a quantum chemistry problem, and in particular molecular vibrational quantum chemistry problems is something that we are starting to learn about and looking into also with chemists. And we are particularly interested in the so if it's just single photons doing linear operations, then it's boson sampling type of problems that may be computationally hard, but we are particularly interested in anharmonic aspects. So can you have anharmonic vibrationals? Or can you simulate anharmonic vibrational dynamics? And how do we produce anharmonicity? How do we produce nonlinearity in the system? Of course, the quantum dot, again, is the nonlinear medium. So if I take a quantum dot, I scatter off a single photon, it will reflect with beta squared efficiency. If I take two photons, then if beta is very close to 1, then it cannot scatter both of the photons at the same time. So actually you'll have like a photon sorting type of process going on here, where two photons are primarily, it's a too simplistic picture, much more complicated as you will see. But in a simplistic picture, two photons will be transmitted, one photon will be reflected because one photon is destructively interfering in the forward direction. So you'll get a nonlinear photon sorting type of process like that, and nonlinearity at the single photon level. It's beta again, not anti-phasing, of course. That is the governing parameter. So here we observe this single photon linearity, and in all its complexity, we won't have time to go through it at all. But here we are doing correlation measurement. Okay, so this is transition showing that you're really reflecting one photon at a time. This correlation measurement showing that it primarily transmits pairs of photons. The G2 is above 1. And then you can look at pulse shapes that are coming out that this nonlinear interaction is doing. This is what all this advanced, the butterflies and the pictures here shows their correlation measurement between two different detectors, where we are simply resolving the dynamic of these two photon scattering processes. That's what's going on down here. And comparing it to the single photon scattering processes, where one photon scatters and another subsequent photon scatters, and you are comparing those two processes to each other. You create strong correlations in the two photon scattering processes depending on the duration of the pulse. I can control the length of the pulse. I can make it shorter than the recombination time of the emitter. I can make it much longer. That is what I'm varying down here on the x-axis, and I'm introducing different temporal correlations of the pulses where at the single photon level, where the difference is really 1 or 2 photons. And that is mapping onto anharmonic vibrational properties of molecules, and we're just starting to understand the potential mapping there, and this is just fresh from where we are, one of the directions where we have our heads into at the moment, where we are interested in these kind of things. Yeah. I think I will skip this. And then I will end with this one and say, yeah, I hope I gave you a little bit of my excitement about this platform, and as I always tell people, you should remember that parents always think that their kids are fantastic, so you don't see all the mistakes, and I may be guilty of that. I truly believe that there's a reason to scale this these platforms up, and we see, obvious reasons to and things we can do, and we'll be seeing a lot of engineering going into these platforms in the coming years. We have quite some good understandings, ideas about scaling up for certain applications, and we're developing much more of that. In particular, the quantum computing, we're just scratching the surface now of what does this tool enable in terms of measurement-based quantum computing. What are the engineering challenges looking forward? Well, one engineering challenge is that I didn't tell you about this at all, but actually what we start with is quantum dots that are spread out on a surface or in a substrate. They are randomly distributed, and I make nanostructures around them, and then I just search for quantum dots that couple very well in the waveguide. It's not such a big problem, it turns out, because these waveguides are spatially very robust and spectrally very robust, so I have a very robust nanostructure that I put around. But of course, when I'm starting to scale up to take multiple emitters, this searching around eventually will kill you. So you need to position the quantum dots inside the nanostructures. And this is just our work. I'm just on this direction where you are positioning. It's not just us, many others are doing stuff like that, but you are making nanostructures. You're finding quantum dots with very high precision optically, and then you are engineering a nanostructure around these quantum dots that are located with sub-wavelengths precision first. There's a question about how to excite multiple emitters, because somebody asked about this also. This pi pulse control both of the spin pulses, but also of the excitation pulses of the quantum dot. You need to come with a microscope objective and do quite some alignment and control of that in order to get all this nice performance that I was talking about. How does that scale up when I need to do 5 or 10, or I need to, align all this? And that, so it would be really nice if you can excite directly through the structures. If all I have to do is to send light on a grating, and that would be coupled into a waveguide, and I could distribute this pump light into various different devices and excite the quantum dots through the waveguides. I would make all this alignment stuff much, much more easy. And we have some nice stuff on this direction as well. Even some patterns on this, where how you can personally excite through the waveguides with some clever designs. And then I think the big challenge really for the field is this multi-emitter thing. Couple multiple quantum dots, having local tuning capabilities of these quantum dots to tune them into resonance, overcome even the slow drift or feedback, or even the slow drift, so that you get truly transform limited lines in the nanostructures deterministically coupled to each other, and so on. That's to scale up to multiple emitters, because the quantum computer will not be one quantum dot emitting many photons. You need multiple quantum dots. We can discuss how many. It doesn't need to be really many, but you need to work and improve this even further. And I think in UK we have quite some work on this. On the way in this direction, it looks promising, but there's really work to going into that to take it to the next level. So this is this is the most important slide. So this is acknowledging all the people. There's a little time to scale up message. But these are this is a group at the Niels Bohr Institute. These are my colleagues that I work very closely with. Anders Sørensen, that I mentioned several times, who is running the theoretical quantum optics group, and we have very, very close collaborations on thinking about the architectures for this hardware. Leonardo Midolo, he's a wizard on all the devices, fabrication, characterization. And then the international collaboration, Richard Warburton here in Switzerland, Basel, on all the spin physics and quantum dot physics, and Arne Ludwig, who's growing all this very advanced heterostructures that makes this all possible. So I think I'll just stop here, and happy to take further questions. So thank you very much for staying awake.
Thank you very much. Thank you very much. much, Peter, for this very interesting insight into photonics and quantum computation that you can do with photonics. Some Swiss chocolate for you from Switzerland.
Thank you very much.
I hope you will appreciate it.
Absolutely.
Are there any questions? There are lots